Great. So it's now 3 p.m. and welcome to the last Common NLA session of 2020. We're going to have a very nice talk today, and then because we've only got one talk, we're going to have an extended gather session. So please join us there if you can. Today on Zoom, Minhong will be managing questions there. Hi, Minhong.
Hi.
And Hassam will be managing questions on YouTube. Hi, Hassam.
Hello.
So as a reminder, if you have any questions, please put them either in the Q&A on Zoom or in the chat function on YouTube. And feel free to ask more at the gather session afterwards. Great. Okay, so today's talk is coming from Alice Cortinovis, who is a PhD student at EPF Lausanne. And she's going to be telling us about randomized trace estimates for an indefinite matrices with an application to determinants. So Alice, take it away. The stage is yours.
Thank you for the introduction. Let me share my screen. Okay, so today I will talk about randomized trace estimates for indefinite matrices with an application to determinants. And this is joint work with my PhD advisor, Daniel Kressner. So the problem that we considered is the approximation of the log determinant of a large symmetric positive definite matrix A, which we assume to be available only through matrix vector multiplications. And such problems arise in a variety of applications, for example, in Gaussian process regression, in lattice quantum chromodynamics, Markov random field models, and in graph theory, where some quantities, such as the number of spanning trees, can be written as the determinant of a suitable matrix. So this log determinant computation is related to trace estimation via this formula here that says that the log determinant of a matrix is equal to the trace of the matrix logarithm of A. Now, there are several ways to estimate the trace of a matrix, which is available through matrix vector multiplications. And we considered the Hutchinson trace estimator. So this is based on the fact that if we take a random vector X, whose entries have mean 0, are uncorrelated, and have variance 1, then the expected value of the quadratic form X transpose Bx is equal to the trace of B. So what one can do is to take, let's say, capital N copies of samples of this vector X and compute the quadratic forms and then average them, and use this as an approximation for the trace of B. So the result is very general, but usually what people do is choosing X to be a standard Gaussian random vector or a Rademacher vector. So Rademacher vectors have entries, independent entries, which are plus or minus 1 with equal probability. In this talk, I will restrict to, I will consider Rademacher vectors. So the approximation of the log determinant that we consider is an average of capital N quadratic forms involving the logarithm of A. Now, there are two issues with this. So first of all, even if the matrix A is symmetric positive definite, in general, the logarithm of A is indefinite, and most existing analyses and tail bounds for trace estimation only address symmetric positive definite matrices. The second problem is the computation of these quadratic forms involving the logarithm of A. The fact is that we can only do matrix vector multiplications with A. So these quadratic forms need to be approximated. And what people have done is to substitute, like to use a polynomial instead of the logarithm. And this polynomial can either be a Chebyshev interpolation polynomial or a truncated Taylor expansion of the logarithm, or this polynomial approximation can be done implicitly via Lanczos method, so, like in this paper here, and we will follow this second approach. So first, let me talk about tail bounds for trace estimation. So we will denote by trace n of B the average of capital N quadratic forms, where these xi are Rademacher random vectors. And we have this result here that says that if we take a number of samples larger than 6 over epsilon squared times the logarithm of 2 over delta, then the relative error in computing the trace is larger than epsilon. I mean, the probability that the relative error is larger than epsilon is bounded by delta. Formulating this, we reach a relative accuracy epsilon with failure. And now the problem is that for the indefinite case, we cannot expect a bound on the relative error because the trace could be 0, but the estimator is not 0 in general. So there is this result here that exploits the fact. So, okay, so to get this result, one can rescale A in such a way that the logarithm of A becomes symmetric positive definite, and then apply the previous theorem. In this way, one gets an estimate. One gets an accuracy epsilon with failure probability delta for this number of samples here. Note that the number of samples grows quadratically with lowercase n, which is the dimension of the matrix. So, and this is suboptimal because actually, if we look at this quadratic form, if we take xi to be a canonical basis vector, we can recover exactly one diagonal entry of B. So with small n of these quadratic forms, we can actually compute the trace exactly. So we wanted a bound that holds for indefinite matrices without needing the symmetric positive definite result. And there's this Henson-Wright inequality, which is exactly what we need. So it's a concentration bound for quadratic forms, and it holds in general for sub-Gaussian vectors. The problem is that we wanted a specific result for Rademacher vectors with explicit constants. So what we got is this result here, that if B is a matrix with a symmetric matrix with 0 diagonal, then the probability that this quadratic form, so only one quadratic form, the absolute value of one quadratic form is larger than epsilon, is bounded by this quantity here. So this assumption that the diagonal of B is 0 is just to make the statement shorter, but it's not a big deal. So briefly, the idea of the proof is to bound the entropy of this random variable using logarithmic Sobolev inequalities, and this follows an argument in this reference here. Then we can get a bound on the moment generating function, and then use Chernoff bounds to conclude. The constants that we get, okay, we don't know if the constants are optimal, but at least they're a bit better than what's in the literature as far as we know. So this is the result for one sample, and we want a result for trace n of B, which is the average of capital N quadratic forms. To do this, actually observe that we can write this average as a quadratic form itself, involving a larger matrix of dimension capital N times small n, with this vector here, which is a concatenation of Rademacher vectors, so it's itself a Rademacher vector. Then one can just plug in the result in the previous slide, and we get that this estimator has an accuracy epsilon with failure probability delta for this number of samples. So we still have the dependence on the logarithm of 2 over delta and of 1 over epsilon square. We have a dependence on the norm of B. And then we have this factor rho, which is the stable rank of B, which is defined as the ratio between the squares of the Frobenius norm and the spectral norm of B. And this stable rank is between 1 and n. So let's say the estimate is better if the stable rank is lower. Here are some remarks. So first of all, this worst case dependence on n is unavoidable because there are actually some matrices like this one, for which the estimate really depends on n. Second, the stable rank plays a crucial role in the required number of samples. In particular, we're happy if we have a small stable rank. So, and we will see later that there are some classes of matrices for which we can say that the stable rank is low. So we can get a good accuracy. And finally, we can actually get a result for symmetric positive semi-definite matrices from the result for indefinite matrices. So if B is symmetric positive definite, we can divide by the trace because it's different from 0, and we get a relative accuracy epsilon with failure probability delta for this number of samples here. So here it appears a rho to the -1, so this stable rank to the -1, which can be as small as 1 over n. So this result improves the one I showed you before by roughly a factor rho to the -1. So this addresses the trace estimation part. And now we need to approximate the quadratic forms involving the logarithm of A. And we follow the same approach as in this paper. Basically, to approximate each one of these quadratic forms, we run m iterations of the Lanczos algorithm with starting vector x1 or xi, I mean the right one. And it outputs an m by m tridiagonal matrix, symmetric. Then we take the logarithm of this small m by m matrix, take the entry in position 1, 1, and then multiply it by the square norm of the initial vector, which is actually n in our case. So the reason why this makes sense is a connection to quadrature. In particular, this quadratic form x transpose f of a x can be seen as an integral of f with respect to the spectral measure of A. And it turns out that doing Lanczos method and taking that approximation corresponds to Gauss Quadrature Rule with m points for this integral. So as a Gauss Quadrature Rule is exact for polynomials up to degree 2m minus 1, we can turn polynomial approximation results of the logarithm into an error bound for our approximation, which is this one. In particular, the error after m iterations of Lanczos method is bounded by this quantity here. And okay, so this is the important term, is it depends on the condition number of A, and it decreases exponentially. So with these two ingredients, we can get an error bound for the final approximation. So recall that this thing on the right was the quantity we would like to have. And this on the left is the quantity that we actually compute. I mean, we want to estimate the error of this quantity here. And combining the previous results, we can show that this approximation has accuracy epsilon with failure probability delta if we take this number of samples So this has this row here, which is the stable rank of basically the matrix, which is logarithm of A, where the diagonal is zeroed out, and this number of Lanczos iterations. So basically, this means that the number of samples at most grows linearly with n. And if we know something more about the stable rank, we can say something better. So as an example, so there are some classes of matrices for which the stable rank is low. In particular, for example, if we take a regularized kernel matrix of this form here, where C has quickly decaying singular values. For example, C could be the discretization of a one-dimensional radial basis function kernel. Then the stable rank of this matrix in which we're interested in is constant when we increase the dimension n. And this means that to get an accuracy epsilon for the log determinant with failure probability delta, one needs a number of matrix vector multiplication that grows logarithmically with n. And everything I said until now was for Rademacher vectors. Everything also holds for Gaussian vectors, basically up to changing some constants. And the only thing is that in this last part, in this combined result, one needs to be a bit careful because the Gaussian vectors are unbounded. But yeah, at the end, the results look similar up to constants. So to sum up, I presented some new asymptotically optimal analysis of stochastic trace estimation for indefinite matrices, and in particular for the log determinant. And all our estimates get better if the stable rank of the logarithm of A is lower. What would be nice would be to improve the dependence on epsilon, because for now we need n proportional to 1 over epsilon square. So this has been improved in the symmetric positive definite case in this recent paper. It would be cool to do it also for indefinite case, maybe combining with other techniques. So if you're interested, we have a preprint on arXiv. And yeah, that's the end of my talk. Thank you for your attention.
Thanks, Alicia. That was a really interesting talk. I don't think we've got any questions at the moment, but I'll start with one. So a lot of your results depend on the properties of the matrix A itself. And you gave an example where you have this low stable ranks, you'd expect nice performance. How likely is that in practice?
I think it really depends on your application.
Mm-hmm.
If you have some insight, I mean, another case in which the stable rank is low is if you have some big singular values and then the other ones are negligible, and maybe you don't really know how many big ones you have, but they're not so many, and then it works.
Right. Okay. Yeah. So there's some classes where this is going to be really helpful, basically.
Yeah.
Okay. Cool.
And then actually, okay.
Oh no, go on.
No, I mean, you can do some a posteriori estimates and see the variance of your estimator, and this also gives you an idea of like how well you're converging. So you can somehow get an estimate of the stable rank a posteriori somehow.
Mm-hmm. Cool. Thanks. Minhong, do we have any questions on Zoom?
Yes, there's a question from Nicholas. What is the hope for the complexity in epsilon?
Okay, so the hope would be to improve from epsilon to the -2 to epsilon to the -1. I mean, it's really a hope. I don't know if we can do that.
Great. And Hassam, do we have any more questions on YouTube?
Yes, we have 2 questions on YouTube. So the first is, what are epsilon and delta in practice? So these questions are asked by Catherine Lund.
What are epsilon? Okay, so delta can be arbitrarily small. Okay, so let's say delta can be 10 to the minus 6 or so. And so this is the failure probability, and it can be made smaller because the dependence is like log of 2 over delta. So that's fine if delta is really small. And epsilon actually is quite big, can even be larger than 1. Yeah, I would say that in general is order of 1.
Okay, so the other question is, what is the condition number of A in practice?
It really depends.
So she asked for some of the applications you mentioned at the beginning.
Okay. In general, I don't have a precise idea, but for example, for regularized kernel matrices, there's the regularization parameter that keeps the condition number under control.
Okay.
So like if you regularize a lot, then the condition number is lower, but then, I mean.
So I have a question. For example, so the estimation requires this, you call them the Rademacher vectors.
Yes.
Or generally, so would that be possible? I mean, the idea is, can you improve the conditioning by introducing some preconditioner, for example? But then that will change. I believe that will change the distribution of the vector. Would that be possible?
I don't know. So how would you? So you would use some different vectors instead of Rademacher vectors, basically.
Yeah, I mean, so you're computing X transpose AX.
Yes.
What if you compute X transpose M minus half A M minus half transpose X?
Yeah, so I don't know exactly what happens. I guess as long as you can keep the distribution of the new random vectors under control, maybe you can get similar results, but I don't know.
All right, thank you.
Great, I think that's all the questions. Thank you, Alice, for an excellent talk and discussion. And before we move over together, I've just got a couple of things to say.
Okay, I'll stop sharing.
Great. So first of all, thanks to everyone who's participated in NLA this term. We've had some really great talks. There's really great talks and really good discussions in the Gather session. We haven't fully worked out what's going to be happening moving forward, but we're meeting to discuss that. So keep your eyes open on your inboxes and on our website to see what NLA in 2021 entails. But there will be some things going on. Yeah, so thanks everyone. Thanks, Alice, and hopefully see you in Gather. And if not, have a great winter break.